Good day everyone. I am Abubacar Asma Abubacar. So today I'm going to present my chosen research article entitled Modeling Damped Oscillations of a Simple Pendulum Due to Magnetic Braking by Onofre B. Perry. So before that, let me give the definition of some keywords in this study that I will be mentioned later. So the first one is the Lenz's law. So Lenz's law is one of the essential topic in electrodynamics. State that the induced electromotive force with different polarities induce a current whose magnetic field opposes the change in magnetic flux through the loop in order to ensure that the original flux is maintained through the loop when current flows in it. So the second one is eddy currents. So eddy currents, also called as focal currents, are loops of electrical current induced within conductors by changing magnetic field in the conductor according to Faraday's law of induction. So eddy currents flows in closed loops within conductors in planes perpendicular to the magnetic field. So the third one is magnetic braking. So magnetic braking may refer to eddy currents, which is the use of magnetic induction to stop or slow a moving object. So now let me give an introduction for what is physics behind in this study. So magnetic braking or damping due to magnetic drag force is a consequence of Lenz's law. So this paved the way for a range of experimental and theoretical presentations in the literature. So the most familiar among those experiments perhaps is the slowing down of permanent magnet moving through a non-magnetic but electrically conducting tube such as an aluminum pipe. So this method, however, is limited by the fact that the moving magnet is hidden from view. So as representative solution to this drawback, the motion of a magnet sliding on an inclined plane inlaid with a non-magnetic but electrically conductive plate has been presented. So in this paper, the motion of a magnetic simple pendulum where its bob is a permanent spherical magnet is in the very close to aluminum sheet. So wherein, similar to the case of the other studies, electromagnetic induction entails that an electric current known as specifically as eddy current is generated in the non-magnetic sheet. So Lenz's law then dictates that the associated magnetic field of the eddy current opposes the magnetic field of the magnet in motion. So this places a damping force on the magnet, thus the magnet braking. So apart from what appears to be another exciting demonstration of Lenz's law, this study is an effective demonstration or laboratory exercise on damped oscillations. So this presents a result via experiment which are fitted to the theoretical model. So the following are the materials used in this study. So the first one is aluminum sheet, simple pendulum, smartphone either with low or high speed camera, computer running MS Excel, and tracker. So this figure shows the simple setup for the experiment, wherein the outer position the pendulum bob as close as possible to the back surface of the baking pan. So and allowed oscillation at small angle. Aside from preserving the simple harmonic nature of motion, the small angle oscillation also helped to ensure a relatively uniform height of the bob from the surface of the baking pan. So the motion of the magnetic pendulum was recorded using the smartphone camera and then loaded into tracker in order to generate the position time data points. So with the origin of the coordinate system being the points of subvert of the pendulum. So this figure is the plot of the angular position of the pendulum as a function of time. So same as this one is the plot of the horizontal position of the pendulum as a function of time. So same plot reveal on the apparent case of exponentially decaying oscillation. So for the theoretical model of this study, so since the oscillation of a simple pendulum or a slow type of motion, this paper modeled the magnetic braking force to be linearly proportional to the speed. So that is the damping force F sub md is given as this equation. So negative bv, where b is the magnetic damping coefficient that depends primarily on the strength of the magnetic field of the magnet and the conductivity of the non-magnetic plate where eddy current is generated. So this figure shows the forces with direct bearing on the motion of a simple pendulum of mass m and length l, so whose motion is being resisted by a drag force linearly dependent on the speed. So again, this shows the forces that affect the motion of the pendulum. The variable x and y are horizontal and vertical position of the pendulum with respect to the origin identified as this point P. So theta is the usual notation for the angular position of the pendulum relative to the equilibrium position. So in this study, the drag force is the magnetic damping force, considering E as a unit vector tangential to the arc length S. So from Newton's second law of motion, this yields from this equation, so mv squared s over dt squared of E is equals to negative mg sine theta E minus b derivative of s with respect to theta E. So this can be written as this second equation. So using s, or the arc length s, is equals to L theta, and imposing sine theta equivalent to theta, as well as dividing both sides by m, and then letting the gamma equals to this one, wherein gamma is just the damping ratio, equals to b over 2m. So and omega sub o squared is equals to g over L. So this equation can be written as this equation, so which has the auxiliary equation as of this form. So q squared plus 2 gamma q plus omega sub o squared is equals to 0, so which has the root q sub 1 equals to this form and q sub 2 equals to this form. So thus the general solution of this equation 5 can be written as this form. So theta as a function of t is equals to e to the negative gamma of t, a sub 1 e to the positive square root of gamma squared minus omega sub o squared plus a sub 2 e to the negative square root of gamma squared minus omega sub o squared. So where the wherein the a sub 1 and a sub 2 here are the arbitrary constant. So this solution has three cases. So we have case 1, wherein omega sub o squared is greater than the gamma squared, means we have oscillatory and underdamped. So for case 2, omega sub o squared is equals to gamma squared, we have not oscillatory and critically damped. The third case is we have omega sub o squared less than the gamma squared, so not oscillatory or overdamped. So case 2 and case 3 are both without oscillations, while case 1 on the other hand predict exponentially decaying oscillation. So by making substitution, this equation indicate that the exponential inside the parentheses of the general solution are not real. So therefore this can be written as this form. So the using Euler's relations, we have this form. letting b is equals to I times a sub 1 minus a sub 2, and c is equals to a sub 1 plus a sub 2, this equation takes the forms of this equation 12. So the initial condition and the velocity of the damp oscillation determine the constant b and c. So in terms of the angular amplitude theta sub o and the phase angle, the equation 12, the previous equation 12 here, can be written as this form. So the horizontal position x as a function of t of the pendulum of line L can be written as this equation. So from the first provided figure, the horizontal position x of t of the pendulum of length L can be written as this one. So writing the horizontal position amplitude x sub o is equals to L theta sub o. The horizontal position of the pendulum as a function of time has the form of x of t is equals to x sub o e to the negative b over 2n times t cosine of omega prime t plus p. So the results are presented in this two figure. So this figure shows the experimental data and theoretical data for angular position as a function of time. So the second one is the shows the experimental data and the theoretical data for horizontal as a function of time also. So this reveals a satisfactory match between the theory and the experiment. So for the results of this study, so accordingly, the obtained fitting parameter as shown in the figure, shown in these two figures, shows that the condition, the first case, omega sub o squared greater than gamma squared for the underdamped oscillation is comfortably satisfied in both models for the angular and horizontal position. So the length of the pendulum was 46.5 cm. Therefore, this particular data model match showed that the oscillation of a simple pendulum under influence of the magnetic braking, although the results might be different for magnets with far stronger magnetic fields, conforms to the case of an underdamped oscillation. So with the damping force being a linear function of the speed. So and lastly, for the application and future outlook of this study, the special application of this study is that it helps us well for a slow cost demonstration setup for lens law and magnetic braking, and also by this simple experimental setup, we can easily demonstrate the damped or underdamped oscillations in undergraduate class in classical mechanics. So while for the future outlook of this study, again, this study will help us to demonstrate the damped or underdamped oscillations using the experimental setup used. So and this paper might be adopted as a full laboratory activity on damped oscillation. So that's all for my presentation, and